Hello, my name is Brad Childs. I work at Red Hat. I'm the development lead for storage volume enablement on Kubernetes. If you were next door earlier, you would have seen Jan Safranek give a talk on external storage provisioning. And in typical Kubernetes fashion, it was kind of scheduled out of order, and we did the deep dive there, and we're going to do kind of the general overview of storage features here, and hopefully, the system becomes consistent. So kind of a brief roadmap. We started with the basic volume plugin framework at the initial launch of Kube, and that's a very specific specification of the volume that you're going to use in a pod. And since then, we've added features around, we've added different volume plugins. We've added dynamic provisioning in alpha. We've added dynamic provisioning in beta. We've added volume selectors. We've added security. We've started adding external provisioners, and that's pretty much what we're working on right now is external provisioners. But I'm going to go over the StorageClass and the dynamic provisioning aspects of this, and also pv-selector. And I'll go through some basic usage scenarios and also kind of show how it works in the framework itself. So start off with the volume plugin framework. This is the most basic way to use storage, and really there's no abstraction between the developer and the backing storage. There's quite a few different volume types supported, and these are all types that are also supported in the persistent as a persistent volume. But you would specify your volume properties directly in your pod, and you just get a direct connection to your volume. With persistent volumes, we actually have an abstraction between the storage and the user, and it's enabled an administrative role and a developer role. So we actually have a separation of concerns. The administrator will create persistent volumes, and they'll register the persistent volumes in a pool. The developer will create claims against the persistent volume, and this level of abstraction allows the developer not to have to know about storage. It also facilitates portability between pods and the actual infrastructure they're running on. So you don't have to, with the volume framework, if you have your NFS server specified as an IP with an export, if you were to move that from on-prem to cloud, you'd end up having to have the exact same connection details in cloud. With persistent volume and a claim, you actually have a layer of abstraction, and the claim can be something else on a different cloud provider. So we have the concept of developer-owned assets and administrative-owned assets with persistent volumes. With persistent volumes, we have a binding controller. This wasn't so much an issue with just regular volumes. The kubelet would handle the mounting of the storage. But now that we have two different objects that have to be linked together, we have a controller that maintains the life cycle between that. The volume binding controller is responsible for binding, provisioning, and recycling persistent volumes, and this is pretty much the entire life cycle of a persistent volume. And when it's doing its matching, it's done primarily on size and access mode, and then some of the features that we've added recently, like label selectors and StorageClasses, has increased what it will actually match on. So here's the basic flow for binding a persistent volume. So we have a binding controller. This is part of the Kube framework. It starts as when you start your Kube controller, the binding controller starts, and it sits there listening for persistent volumes. The first step, the administrator will create persistent volume objects, and the persistent volume object is the actual specification and details of the backing storage. So if it's NFS, it'll be an IP and an export. If it's cluster, it'll be an IP and a volume name. Just depending on the details of what your storage you use, like the persistent volume spec is very specific to that backing storage type. So step one, the admin creates the persistent volume with the volume details. Step two, a developer goes and creates a claim. The claim has the basic request that the user needs for storage. In the most basic scenario, they'll ask for storage of a certain size, and they'll specify an access type. So you have read-write once, read-write many. Read-write once means that it can be used once in a pod. Read-write many means it can be used multiple times, by multiple pods, but not outside the namespace. So it's kind of an alias for shared storage, shared network storage, whereas read-write once tends to be like block storage. And then after step number 2, when the dev creates the claim, the binding controller will look at the claim and it'll search through the persistent volume pool and find something that matches it and actually bind the claim to the persistent volume. The binding is done as a 2-transaction write. So we have a tight linking of the PV and the pv-c. This is somewhat unique in Kube. You really, in a HA environment, you want to keep the transactions to a minimum. 2 writes is pretty luxurious, but it was essential for actually linking the 2 objects together. And we start off by writing the pv-c, or start off by writing the pv-c to the PV claim ref. So the PV gets a stamp of the pv-c that claimed it, and then the pv-c volume name gets set to the PV name. And then during these 2 writes, if a version error occurs, we know that some other controller was trying to write the object. The user may have deleted the claim. They may have deleted the persistent volume. We have roll forward scenarios for that. We also write annotations during some of this stuff, so we know if it's the binder doing the writing, or if a user came in and wrote it, or if something else caused the objects to change version unexpectedly. But we have a very much roll forward error recovery if our transaction writing fails. So that goes, let's talk about the new features. So labels and selectors is a feature that we added recently. It's quite similar to node labels and node selectors. The idea is that you tag your labels with, or you tag your volumes, your persistent volumes with certain labels. Then you use match criteria on your pv-c to, essentially match the 2 together. Right now, the administrator is supposed to communicate the values and the ranges to the user. This is kind of a cumbersome user experience. We're kind of in the process of thinking of how to fix this. It's a similar issue to Node, but if you really have 2 distinct users, the developer isn't supposed to see the persistent volumes, so it's a little hard for them to discover what labels or values they might have. It's kind of on the admin to communicate what those labels are. Typically, a lot of this stuff is automated and scripted, so the end user probably doesn't see what the labels and selectors actually are. So the binding controller. This is very similar to the original binding controller where it was just matching on size and access mode. Step number 1, admin will come in and create a persistent volume. They'll create it with a label. This will go into a persistent volume pool. Then step number 2, the user will create a claim. They'll have a selector with their match label and then the label and the value that they're looking for. And then step number 3, the binder will come and actually search the persistent volume pool for a matching volume, and then it'll go through the same 2-step process to bind the volume with the claim. So nothing new here except we add like a new match criteria for actually binding the volume and the claim. So labels and selectors, some of the stuff you can do, there's equality. You can combine with the comma, so comma is basically your and. You have set-based, you can do value in a set, you can do value not in a set, you can do value comma, meaning like is the value set, and then you check if the value is in the set. Pretty simple stuff. You can make it as complicated as you want by anding expressions together with a comma. Some examples, you may want to check if backup equals daily. Check if backup, so if you set your persistent volume with a label backup and the value daily, you could, in theory, want the claim that you bind to your pod to be backed up at a certain interval. And maybe you don't necessarily want it backed up monthly or yearly, but you do want it backed up daily, hourly, or weekly. So this is one potential use case. Another possible one, production and staging. You don't want this particular pod or application to land in a production or staging environment. So you could use selectors here. It could also be used for GID and security. It's really up to the administrator to define how they use labels and selectors, and then for the users to kind of comply with this. But it's very flexible. It just offers additional match criteria for volumes and claims. So the next feature, StorageClass. This one, it has some overlapping function with labels and selectors. A lot of this was added in anticipation of enhancing our dynamic provisioning framework. StorageClass really represents a set of properties that all PVs in the StorageClass belong to. The StorageClass properties don't have explicit meaning to the framework, but it's something that the admin or the developer kind of agrees upon has value. Typically, it's like performance characteristics. It could be security. It could be backup policy. It could be really anything that you want it to be. Each claim can have a single storage class. Each volume can have a single storage class. And it really facilitates dynamic provisioning. And storage classes can be used for pre-created or dynamically provisioned persistent volumes. And I'll show examples of both of those. So here's the YAML for it. So this is the actual object you would create when doing a storage class. Pretty simple. The parameters are string, so anything could go there. The name is important. The name will have to be specified in the claim and also the persistent volume. And you can see here is this annotation. That's how the volume matches to the storage class. And then, like I said, the parameters, anything you want, they really have meaning probably to whoever is provisioning the volume. Should it be dynamically provisioned or statically provisioned? So similar use cases to labels. It could be backup policy. It could be volume performance characteristics. You could have unique file system properties that you want to select for, say the file naming size, if a file system supports extended attributes. Maybe there's consistency modeling. You want to say that one particular storage class has strict consistency, the other one, the consistency is relaxed. There may be provisioner configuration specified in your storage class, and this is parameters that actually go to the provisioner when it's creating a new volume of that particular storage class. Or it could also have some security information supplied. But again, the framework doesn't care about the properties so much. These are really meanings that's communicated between the developer and the administrator. So the flow of persistent volumes with a binder and claims. In this example, it's just showing statically provisioned persistent volumes belonging to a storage class. There's no dynamic provisioning yet. I'll show that in a minute. But it's a very similar flow. The admin will create a storage class. They'll create persistent volumes, and when they create the persistent volumes, they'll associate it with the storage class they created is step number 2. Step number 3, the user will create a claim, and in that claim, they'll specify the storage class that they want. Then the binder comes in. It'll search the persistent volume pool for a volume that matches on size, access mode, and storage class. So those 3 characteristics. And finally, the binder will go through the 2-step process, the 2-transaction process, to actually bind the volume to the claim. Real simple stuff for this one. But this gets us to something more interesting, which is dynamic provisioning. So dynamic provisioning is the automatic creation of volumes. So it could either be a cloud provider creating the volumes, it could be a standalone application creating the volumes, it could be somebody locked in a cage that creates the volumes. It's really anything, but it's really done at the time that the claim is created. In our alpha version of dynamic provisioning, we had a single provisioner per cluster, and it was really only supported by cloud providers, so AWS, GCE, Cinder. We had provisioners there, but you could only have one provisioner in the cluster. But with storage classes in our beta release of dynamic provisioning, we really enabled multiple provisioners per cluster. And with multiple provisioners, you could have different properties for your provisioner. If you're in AWS, it allows you to have SSDs versus spinning disk. You could have different, you could specify the IOPS or different performance characteristics and divide your persistent volumes up by those different properties. And then you also have in-tree or out-of-tree provisioners. So there's a distinction there. Most of the in-tree stuff right now is cloud provider. Our in-tree stuff does support multiple provisioners per cluster in-tree, and then out-of-tree, you can also have multiple provisioners per cluster, and you could even have a mix of these. So you could have 5, 10, 100 storage classes per cluster. It really doesn't matter. And they could be a combination of in and out-of-tree. So the flow for users requesting storage of a storage class is really through the claim. The claim's the user-owned object. So pretty much any communication the user does with the framework is through the claim. They'll create a claim, and then the binder will look and check if there's a type that matches the claim in tree, and if so, it'll call the provisioning method that. If not, it'll wait and let an out-of-tree provisioner, which Jan demoed earlier, actually do the provisioning. And the provisioner will is supposed to create the volume based on the storage class. So it's really up to the administrator to make sure that what's being provisioned is what's specified in the storage class. So here's a list of our in-tree provisioner types. We have Cinder, AWS, GCE, Azure, vSphere, GlusterFS, RBD, and Qubite. I'm not sure how to say that. But all this stuff is baked in tree. You don't have to do anything when you start Kube. If you have storage of this type, it's already there. You don't have to stand anything else up. We hope to get this out of tree soon. I mean, it's on the storage SIG roadmap to move some of this stuff out of tree. And that's somewhat of a maintenance thing. It's also kind of as a proof of concept because we'd like all provisioning. And eventually, most of the volume types moved out of tree. So I put on here some of the actual YAML for each one of the in-tree provisioner types, and this is probably more for reference. I'm not going to go over it right now, but it represents the parameters that each one of the in-tree provisioners will actually accept, and you could tweak these depending on what you actually wanted out of your storage class. So kind of as a quick example, let's look at the GlusterFS one. So you have your REST URL, your user, your secret name, and secret namespace. Maybe you have multiple Gluster backing storage providers, and one's slower and one's faster than the other. You'd create 2 storage classes, and they would have different REST URLs and then different users and different secrets. And that's pretty much goes for all the rest of them. There's other parameters you can tweak with, depending on the backing storage type. So the in-tree dynamic provisioning flow, quite similar to the other stuff. We have the administrator creating the storage class. We have the binder in this scenario, just sitting there listening, starting up as part of the Kube framework. The user will come in and create a claim, and they will specify a storage class in their claim. The binder will see that storage class and recognize. They'll actually go and look at the storage class objects, find the one with the matching name, look at the provisioner type, and then if it recognizes that it's an in-tree provisioner type, it'll make a call to the volume plugins provisioning method, and that provisioning method knows to go out and call out to the cloud provider to create the actual volume. And then the provisioning method also creates the persistent volume object as step number 5 and puts it in the volume pool. And while it's doing that, it links the persistent volume and the claim at the same time. So the binder's creating the persistent volume and binding it to the requesting claim kind of in the same step. And that's so something else doesn't come along after the volume's created and claim the resource. So out-of-tree provisioners, if you were at Janstock, you went over this pretty extensively. They can run as a standalone application. There's no specification of what they have to be. It could be Java, it could be C, it could be Golang, it could be shell script. Basically whatever you want, but it needs to be able to communicate to the API server. It'll listen for events from the API server. It's meant to listen for new claim events. And then, of course, provision storage based on the provisioner type that it recognizes. The recent changes we've added put the provisioner type in the claim, right? So they don't actually have to look at the storage class to know if they support a particular claim. Before we had to do like a double reference. You'd have to go and monitor the storage classes, watch for new storage classes, watch for types, and then monitor, or once you see a provisioner type you recognize, watch for storage classes coming, or claims coming in with a storage class of that name. There's out-of-tree provisioners have no explicit call by the volume binder. It's up to the external provisioner itself to listen for the claims and to create storage based on the events coming in. The binder is completely out of the picture in this. And we have a pretty solid example with our NFS provisioner. It's something that we are trying to walk through incubation. And it should be kind of the basis for any out-of-tree provisioners that people may write. Is there a question?
Yeah. What processes do you have in place to make sure the out-of-tree provisioners are keeping their stuff up to date and high quality? Because what can happen, we've seen in other open source projects, they just get their stuff out there, they don't maintain it, and then when it doesn't work very well, they blame you, even though it's not your fault.
Yeah, that's a good question. So we've talked about some certification potentially certifying out-of-tree provisioners. Truth is, we can't really control it. I mean, if it's out-of-tree and a storage vendor wants to write their provisioner, they're allowed to. I think it reflects poorly on the vendor if it breaks. But
we had third-party CI systems that they were forced to use, and if they didn't keep those up to date, we kind of put them in a bad place.
Yeah, so I think that's probably where we'll go. Is we'll end up, if you want to be listed on our external provisioner page of supported provisioning types, you'd have to go through like a series of checks, but we don't have that in place yet. This stuff is, it was committed like 2 days ago, so it's pretty new. Yeah, okay, so out-of-tree provisioners that responds to API events on its own. With the NFS provisioner, we use the Go client library, and we watch the API server that way. Like I said, you could even do this in shell script and just use kubectl in a loop to look for new persistent volume claims and provision that way. So the flow for this, same step, admin creates a storage class. As a second step, they will create or run an external provisioner, and this may be something that runs on a standalone node. It may be something that runs as part of the Kube framework. It may be something that's a completely manual process that sends an email out. It's really up to whoever is authoring the external provisioner how this works. It's important to follow the API mechanism that was mentioned in Janstock. That's how we make sure that the binder knows that the volume that's created by the external provisioner is valid. But how this is actually done is really up to the administrator. So step number 1, admin creates the storage class. Step number 2, they install and launch a provisioner. They'll point the provisioner back to the Kube API server. Step number 3, a user will come in and create the claim. That new claim event will come to the provisioner who is sitting there monitoring the API server for new claim events. And then the provisioner will actually create the physical volume. Maybe that's a call out to Gluster, maybe it's a call out to a cloud provider, maybe they put a zip disk in a drive. They'll do something that creates a physical volume, and then they'll create a persistent volume object that maps to that physical volume. And then as step number 6, during the creation of that persistent volume object, they'll also bind it to the claim. So it's creating the persistent volume and binding the claim is kind of the same process. So here's the slide I was hoping I didn't really have to talk about because it's probably too small for you guys to see. But this is the YAML for a fully bound volume and claim. We have a couple annotations off to the left. These are added by the binder, so we know that the binder was actually the one completing the bind between the claim and the volume, and the user didn't just specify these values when they created the claim. And if they did, there's some use cases where that's valid, but we want to know about it, so if we have to do a recovery step, we can tell if it was the user that created the hard link the two together, if the binder actually did, and we have to do some kind of recovery if there's a failure. We have a volume name here in the claim. At point, since the persistent volume is a globally scoped thing, the volume name has to be unique. And then you see the UID of the persistent volume claim mapped over here to the persistent volume. And that is it. I'm going to open it up for questions. You guys have 1,000 questions or none?
One for sure.
You want to try this thing? No, forget it. I'll repeat it.
It's probably really basic. After step 6, where the volume is bound, let's say it's a Cinder or EBS volume, how is the volume actually consumed by the application or user?
By the claim. So once it's bound to the claim, the user will specify the claim in their pod.
So it's sort of like, there's like an API call for this? And let's say Cinder volume is provisioned, or EBS volume is provisioned, and the application wants to write to it. They're going to mount it on attach it to a VM or something, right? How does that, that's like the user that do all that?
So that's the core claim concept, right? Is like you specify the claim name in your pod, and then you map that to like a directory. So it's specified in the pod. So the claim name is specified in the pod, and that's how you write to it.
So when you're using the internal and external provisioners, on the diagrams you have there, it's always going out to the provisioner first. Does it check the pool to see if there's one there already?
Yes. Yes. So it'll check the pool to see if one already exists, and then if it doesn't, it'll sit and wait for an external provisioner to come in and create one.
Okay. So then, and that's the second part of that question. When you release the claim, even if it came from an external provisioner, it just goes back to the pool.
No, once you release the claim, it's up to the provisioner to delete it. So each provisioner should implement a delete method as well.
Okay, so you can control, so you could have these things with an external provisioner be completely ephemeral, which is they're created, consumed, released, and destroyed, or you could control the policy of when something actually went back in the pool or not.
Yeah, instead of deleting it, you could scrub it and put it back in the pool if you wanted to. You shouldn't, but you could. No resize yet. Everybody wants resize. It's on the storage SIGs agenda for sure, but resize and snapshotting are stuff we're still looking at.
Bunch of debate.
Yes, there's a lot of debate about it.
How does this play or does it at all in local storage?
Local storage isn't something that we've fully realized yet. So we're hoping someday soon to have persistent volumes with local storage. And that's for you want it for like a warm cache or something, right? Yeah. Yep, someday, soon. Other questions? For mirroring, we've lumped mirroring probably in with snapshot replication type of stuff. Depending on the file system you use, it may support it natively. I know Gluster does like replication, so you may get it for free depending on your file system type.
You're talking about the NFS economic creation here in a preference. Would this be related to that?
Say that again? No, we do have an EFS volume type, right? Oh, so he asked if the NFS provisioner would be related to Amazon's EFS. So there is an EFS provisioner, right, in Tree? We don't, we just do EBS? Okay, so no, we don't have support for it yet. Yeah. Yeah. So you could write an EFS provisioner then. Maybe we will after, after we catch our breath from KubeCon. Anything else? You guys are easy. Cool, thanks.